Hey everyone, it's Alicia Panzarella. We're going to be taking a look at chapter 26 today, which is graphing and graphical methods. So I am pretty excited about this chapter. I know that I use graphing, oh goodness gracious, multiple times during the week with my classes, and graphing will be something that you're also familiar with, at least to some degree, but graphical methods is a little bit different, and I will say it is a little bit more specific to content. So taking a look at really what part three of our book is looking at, and it's going to be looking at the visual, graphic, and iconic approaches to problem solving. So the goal, if we see over here, of this specific chapter, and in part three, is really to present, describe, discuss, and exemplify approaches for problem solving that use physical images. So really, we're just trying to get that visual aid. Now, all the techniques involve imagery or visualization in some way, but the focus of this chapter is in mathematics. So the visuals that you may have seen in some of the other chapters didn't necessarily always have a math base, but if we're looking at graphic or graphical methods, it does have that mathematics basis. So looking at the where'd you go? Sorry. Looking at the two parts to this method, chapter 3 looked at graphing itself a little bit more, and then graphical methods is restricted to those techniques that can be used to solve problems either more easily or naturally than by using mathematics or when a mathematical approach is impossible. So if we take a look at just a little bit of graphing 101, couple things to know, and I'm sure you are familiar with the fact that you have to have your x-axis, your y-axis, your x values are always your independent variables, and your y values are always your dependent variables. For you math people, your function or your f of x is going to be your y. For whatever reason, I have found that even seniors in physics, first couple weeks, always have a tendency to forget this fact. So if you are thinking about graphing within your classes, you may want to make sure that they know that x is the independent and y is the dependent. Now, you can have a couple different types of graphs. For science, we use a lot of the scatter plots, but you do have the line, the bar, and the pie. So depending on your need, you will use that different chart or the different plot depending on what you're trying to get across. What are you trying to visualize? If you want to take a look at table 26-1 on page 186, they will provide you with more details about these different types of charts, but you are most likely pretty familiar with these different types. Now, graphs are incredibly useful. Not only just from the visual aid, so you can see, is this a linear trend? Is this a polynomial? Is it a logarithmic? If we're talking from the science point, I always say top opening or side opening parabolic. So seeing that visual and saying, okay, well, if I have a linear relationship, what does that mean for the independent and dependent variable? Or if you have a top opening parabolic, what does that mean? What is actually happening with your independent variable versus your dependent variable? Is there a physical reason why this is happening? So that visualization allows for a pretty broad discussion that you can have with your students, or just in general if you're trying to solve a problem and trying to figure out how are these interacting, why is this happening, what can we do with that information. So you have the visual aspect, but you also have the quantitative information that these graphs also give. So the reason that graphs are incredibly helpful from the quantitative aspect is that you're able to form an equation. Which is really helpful. We know if we want to just plug and chug, which was another chapter within the book, but it also will predict future phenomena. So if you wanted to know at a time of 28 seconds, where is this object going to be? We know that that equation is going to predict that answer. So when we're forming that equation, or at least in physics, we call it the mathematical model, it is going to show the relationship between what could potentially be seemingly unrelated phenomena or a process. Sometimes you can even get that something has no effect. If you take a pendulum, for example, mass has actually no effect. The only thing that has an effect on a pendulum is the string length. And that's something that you can discover through a pendulum lab, through graphing, through an analysis, and an equation will tell you, hey, your slope's actually 0 for the mass. It doesn't have an effect. And it will also readily perceived in understandable fashion. So when you have this graph, you're able to readily see, what's really going on with that relationship. Now, kind of like I already said, the type or form of an equation will also allow for causation to be revealed. If you have a linear trend versus an exponential versus logarithmic, that is going to tell you a lot about what's going on between those different variables. And it also will provide a simple display of the behavior. So again, as soon as you see a linear relationship, you know that you have a direct relationship between your different variables. Or if you have an inverse, that's going to also tell you a lot. So one thing is you want to be sure to recognize and utilize the different types of graphs, especially depending on the level that you teach. You may find that a pie chart is a lot better to represent the information than this would be. So with that, if we're looking at usages in the classroom, at least for my course, we determine almost every equation and every law from a graphical analysis. We pretty much start the course, or I'm sorry, we start the unit we do a demonstration. The kids start to hypothesize what they think is happening within this demonstration, and then they form the lab. They say, this is what I think the independent variable is. This is my dependent. I want to see what's going on between those two different variables. And each group could potentially have different essential questions. Like for energy, there's so much that is involved in the conservation of energy that, every group could look at a different essential question, and then collectively we could make conclusions about energy. Another example is this one right here. We looked at distance versus time with a constant velocity buggy car. The kids didn't know that it was a constant velocity car before they did this. Now, they hypothesized when they saw it moving, but they didn't know for certain that it was constant velocity. Knowing that, and because we got that linear trend and we know that the slope is going to be the same regardless, tells us, hey, this is a constant velocity, and that constant velocity of that specific buggy car was 0.33 meters per second. So that mathematical model or equation can actually tell you very specific things about whatever you're looking at. It also gives you your constant velocity equation, that the final position is equal to velocity multiplied by time plus the initial position, which is what we see here. So equations that, typically may be, just told to them, like, oh, Newton's second law is F net is equal to mass of system multiplied by A. One of the equations for acceleration, maybe you're looking at Ohm's law. These graphical analysis, or just graphing in general, can actually get the students to discover those different equations rather than being told them. Same thing, if we're just looking at, foundational equations, y equals mx plus b, if we're looking at the quadratic equation, you can have where the students run a lab. Maybe they do something that is going to be a linear relationship. Maybe you have, like the example here, where a student will kick the football, and you know that it starts and ends at the same position. So you're able to graph that quadratic formula, or I'm sorry, that quadratic relationship, and then discuss why did you get the formula that you did, and that could lend itself to, hey, here's the quadratic equation. Same thing, like for this example down here, this is a very typical setup to look at Newton's second law. You end up seeing that it is, well, depending on your essential question, you'll either see an inverse relationship or you'll see a linear relationship. But again, you can set up a lab that will discover those things. So pretty helpful from a hands-on inquiry approach using this problem-solving method. Now, if you're looking at something that maybe you don't want it to be purely quantitative, where you're not really looking for an equation, this is really just good to provide visuals in any situation. So if you're looking at your content, maybe, looking at a bar graph is going to be more helpful. Maybe looking at a pie chart is going to be more helpful, especially considering that you can color code, which, depending on what you teach, that color code may be very helpful. Now, graphical methods are helpful when a mathematical option is not available, and really you're going to see it in a 2D representation rather than a 3D, and it's going to really just look at what may be a situation, a 2D representation of what may be a situation or phenomena. So one of the examples they gave was a free body diagram. So if we were in the classroom, this would pretty much just be a ramp. You would have a mask sitting on top of the ramp, so our 3D model. But if you're trying to figure out what is the acceleration of that box as it goes down the ramp, well, this free body diagram will tell you, hey, you have FG parallel pulling down, the force of friction is opposing, so those two forces together are going to interact and produce that acceleration. That's something that's really hard for students, if they don't have a visual of all of the forces acting on the object, they often forget forces and then don't calculate the acceleration right. So graphical methods like this are very helpful to see a whole picture and to see pieces that the student may not see, or really anybody may not see unless they actually had this representation. Now they also are usually used directly to generate a solution. So kind of like I said, this free body diagram is going to help form the F net, or the sum of all the forces acting on the object. So this will form the equation where we're going to generate that solution from the graph, or graphically or indirectly to aid in the mathematics. So we see that with that Newton's second law. Now, there are many other types of graphical methods. However, they're very, very specific to content. So, unless you're looking at forces and you're looking at Newton's second law, which really doesn't happen too much outside of physics or engineering, this really isn't going to be helpful. Same with, Mohr circle, the low deflection diagrams. You can feel free to go to pages 188 and 192 in the textbook to see what these different types are. But like I said, they're very, very, very specific to content. These are pretty high level from what I gathered from the textbook, so I didn't want to spend the time within this video to discuss them. But if you are curious about diffraction gratings, feel free to go ahead and look within page 188 to 192. So really just in summary, the graphical representations clarify the problem and or makes it easier to solve, or I'm sorry, to find a solution. And this may be with graphing, as we've seen, it may be with a graphical method. Even something like this, I can look at that and say, hey, we're looking at V is equal to lambda F. We're looking at a wave property. Somebody in math may look at the same thing and say, hey, that's a logarithmic function. We can look at a real life example of a logarithmic function because we have that graphical representation. So I hope you enjoy graphical analysis as much as I do. And then that pretty much sums up chapter 26.